Modern industrial manufacturing relies on extreme volume to maintain profitability. To manage that profitability, a business must solve a core accounting problem: how to accurately forecast future expenses when production volumes fluctuate daily. Attempting to project costs without establishing a stable baseline yields erratic data. Without a defined set of constraints, cost predictions lack a consistent pattern, making them difficult to verify as output scales. Cost accounting addresses this by applying a specific framework known as the relevant range. Defining this range is the first step in the process. It provides the stable environment needed to build a predictive mathematical model. The relevant range is the specific span of production volume, where cost behaviors remain constant and predictable. Inside these boundaries, per-unit variable costs remain entirely constant. Simultaneously, total fixed costs do not change, regardless of the activity level. These limits are established by real-world constraints: the efficiency of the current plant, the terms of labor union agreements, and capacity limits in supplier contracts. If a business operates outside these established bounds, the standard rules for cost behavior no longer apply. For example, if demand exceeds a plant's maximum capacity, a company might need to lease a second facility. That sudden addition of a new fixed expense changes the cost structure entirely. The relevant range sets the perimeter for cost modeling. Inside these points, linear formulas hold, but crossing them causes those formulas to break down. Within the relevant range, we classify all expenses into two primary categories: variable and fixed. Variable costs are a direct function of production volume. These include inputs like raw materials or the direct labor required to assemble a product. This illustrates the rule for variable totals. Total variable costs start at zero and increase proportionally as production grows. However, per-unit variable costs remain entirely constant. This creates a horizontal line, reflecting the same cost for every unit. Fixed costs follow a different logic. These are expenses that remain unchanged by production levels in the short run, such as rent or lease payments. This graph shows the fixed total rule. Total fixed overhead remains exactly the same, a flat line, even if production halts. But mapping fixed costs per unit, the line curves downward. The cost shrinks as it's spread over more units. This creates a mathematical inversion. Total variable costs scale while unit costs stay flat, whereas total fixed costs stay flat while unit costs fluctuate. Gaining a clear understanding of this relationship is the necessary foundation for identifying more complex mixed expenses in the real world. In practice, operational costs rarely exist in a purely fixed or purely variable state. Organizations frequently deal with mixed costs, combining both elements. Consider a company renting a piece of machinery to increase its production line efficiency. This table outlines the cost structure for that machine. There is a fixed baseline, a flat rental fee of $150,000 that remains unchanged. Added to that is a variable cost of $1 per unit that scales proportionately. The total cost is simply the sum of these two behaviors, creating a predictable formula for the overall expense. Analysts are rarely given a pre-sorted table. Instead, they usually start with a ledger of historical total costs and activity levels. To budget for future periods, we must mathematically extract the underlying fixed and variable behaviors from this historical data. The high-low method is a standard tool used for this type of quick estimation. Using this dataset, we isolate the variable portion by identifying the highest and lowest activity periods, May and July. Dividing the cost difference by the activity difference reveals a $1.875 variable rate. Subtracting that isolates the $400 fixed baseline. This gives us a predictive formula. Total cost equals a $400 fixed base plus $1.875 per machine hour. With this formula, we can forecast future expenditures, such as estimating the maintenance costs for a month with 1,300 machine hours. The models we have built assume that within the relevant range, cost functions are linear. This means costs either change at a constant rate or stay flat over the short run. However, in manufacturing environments, not all costs follow a straight line. We have already seen this with fixed costs per unit, which follow a downward curve as production volume increases. Another exception found in industry is the step cost function. A step cost remains constant over small ranges of output, but increases in discrete, sudden amounts as activity thresholds are crossed, similar to adding a new production shift or hiring an additional supervisor. Recognizing these nonlinear behaviors ensures that financial models remain accurate when production volume crosses into a new threshold. Professionals must be able to identify these behaviors by analyzing how costs change across different activity levels. This dataset shows 4 costs. As units increase from $25,000 to $75,000, cost B stays at $7,500, making it a fixed cost. Cost A increases with volume, but not at a proportional rate, identifying it as a mixed cost. Identifying these behaviors and the ranges where they apply is a core requirement of cost accounting. Mastering these concepts allows for the transformation of historical data into precise mathematical models used to guide future business decisions.